because it's just q to the AB by exponent rules. And so now they've both decided on their secret number, and it's secret because nobody can actually compute what each person's private guess, like private random number is, without doing this fancy logarithm that people have said is hard. Okay. Now, using this sort of key transfer idea, we actually have a way of doing oblivious transfer. Here it is. Okay. Wait, first of all, were there any questions about the key transfer thing, where you both come up with your secret number that you agree on, but you don't, like, nobody else knows what it is?
I mean, I guess the key assumption that you were using is that, like, q in the power of a in the power of b by modulus b is equals to q in the power of b in the power of a.
Yeah.
Modulus b, because, like, multiplication is just reversed, even if it's modulus, right?
Yes.
And, I mean, if you want, I can prove it during my number theory lectures.
That would be
so
great.
I can complement your lecture.
Yeah. Okay. So here's what we have for oblivious transfer. We've got Ginny and Evan. So Ginny has the two messages. Evan has his choice. So basically, Ginny does the same sort of thing as before, where Ginny chooses like a random number and computes. I mean, they have like their public number as well. So that Ginny computes the exponent once again. And then Evan uses his choice, 0 or 1. If his choice is 0, he also computes g to the b. So he's got his secret like number b, and he computes g to the b, like same as before. However, if he chooses 1, then he will compute the number that Ginny just produced, multiplied by g to the b. And then he sends that over, whichever one it is, to Alice, or not Alice, because now it's Ginny. But yeah, so it sends it over, and Ginny uses a hash function and computes either the hash of b to the a or the hash of b divided by a to the a. So if Evan chose this one, 0, then this will come out to be like the actual key to the encryption. However, if Evan chose 1, then this will be the key to the encryption. And yeah, so like what am I? I don't know. I mean, yeah. So you end up with these two keys. Ginny has the two keys.
Wait, I'm sorry. I fail to see why they are different.
Why they're different? The difference is that in this one, Ginny divides b by a.
Yes, but your b would include a in the when c is equal to 1. Oh, wait. So, wait, k0 and k1 are dependent of c.
Yes.
Yes. Okay.
So,
makes sense.
Yeah, Ginny is going to like compute both of these values, but Ginny doesn't know for sure which value is actually going to go with whatever the choice was that Evan made. And so then and he uses these keys to encrypt both of the messages, the only thing that Bob can, or that Evan can compute is the decryption that has the key hash of a to the b. And this is because Evan doesn't know what this value a is. So even though he gave he gave Ginny one of these specific values. The only value of these two that he is able to know is the one that goes along with the one that he sent. So let's think about that. Say he sends G to the B. Then Ginny, there we go, Ginny and Evan. So Evan sends G to the B, and that value is considered to be B. And Ginny computes B to the A and B over A to the A. Bye-bye. So the only one of these that Evan is able to know when he computes whatever, so this is G to the A. So when he computes G to the A to the B, so the same thing as G to the AB, then he is able to know, I guess that would be, yeah. This is either B to the A or B over A to the A, depending on what his choice for the thing that he sends him to. So since Evan chose G to the B as his value for B, when he computes G to the A, B, he knows B to the A, which is one of the keys. But if he tries to know what this other value is, this B over A to the alpha, he could he could do the same thing where he can divide B by A, but he doesn't know what this alpha is, so he can't compute it in the end. But if he sends over, say he sends over A times G to the B, when he sends over A times G to the B, and he gets both of these options back, and he computes G to the A to the B, then this value is actually going to be equal to B over A to the A, because you have to get rid of the A that he already multiplied by. And if he wants to find B to the A, he cannot, because once again, the same thing. He doesn't know what A is set to be. I'm sure there's probably questions, or are there questions?
Sorry, I went to the bathroom, but just to be quick, you basically have to, if I would have to understand what's happening, do I just go over 4 cases?
Yeah. So you just sort of take a look, and you see that no matter what B sends, which B, whether it's G to the B or A times G to the B, the result, because he doesn't know what this A is that he can only, when he computes this key, it only is the same as one of them, and the other one he can't compute.
Mm-hmm. So basically, if it is the same one, it's either yes or no, or if it's different, it means that they disagree, or?
So this one it's not really a matter of whether they agree or not. The whole goal of Oblivious Transfer is to only send him one message, and that message depends on which choice he makes. So using these keys, so Ginny is able to use both of these keys to encrypt each message individually. So the first message goes with the first key, and the second message goes with the second key. And depending on the choice of Evan, either 0 or 1, he computes the different Bs. So he can only compute the key that goes along with one of the specific encryptions because he doesn't know A. Okay. So I just came up with like a very simple idea for a hash algorithm, just like to make it a bit more, I don't know, concrete. In case he is, like before when I talked about a hash algorithm, it's just some sort of weird function that you put some stuff in it and you get a message of like a certain length with basically random numbers. But the cool thing about hash algorithms is that they're not random at all. They're actually going to be, if you put the same input in, you're always going to get the same output no matter what. Okay, so here's the idea. You take your string, just a bunch of zeros and ones. Yeah, and if it's shorter than it needs to be, then you're going to have to add a certain length of zeros and ones. So say I want my output to be like, I want my output to be 4 digits. So this thing is not shorter than it needs to be, so I don't have to add anything. If I did have to add something, then I'd have to have like a preset list of digits that go in a certain order so that I can always like predict what it's going to be, and it's the same every time. If it's longer, which it is, then you cut off the beginning. So I'm just going to erase that part. Then I've got my secret string that is also of length 4. So this one can be 1, 0, 0, 0. This is my secret thing that's just actually built into the algorithm. And you just XOR it. So 1 XORed with 1, you get 0. 0 and 1 is 1, 0 and 1 is 1, 0 and 0 is 0. And there we go, there we have a hash. If you want to know like a real hash, there's one called SHA, or Secure Hash Algorithm. And surprisingly, it doesn't work in a much different way. I mean, you start out with certain strings, certain random strings that are built into the algorithm of a certain length, and you just XOR them with parts of the input at different locations, and there's different padding. But it's really like not like as complicated as you might expect. But it was too complicated to just talk about it right now. Do you guys have any like thoughts about hash algorithms? This one's not super interesting. Because okay, originally I wanted to do like some code that would actually garble some circuits, but then I got confused about like how to take the circuit and like traverse it from the top to the bottom and then the bottom to the top. And so I made like this like silly hash algorithm that I was just going to use because it was just like implementing it real quick, but in the end it didn't like come to anything, so that's okay. This is the question that we answered earlier about like how do you garble circuits that have more than one gate. So like you have bigger circuits that have lots of different ands and ors, and yeah, so you just take the 2 labels that go with the potential outputs. So output 0 and output 1. Each gate has only like those possibilities, and so you just use those as the labels as you go up. Yeah, it's not too bad. And then this is like basically just a cool chart that I saw. There are lots of optimizations to this like algorithm. So when you do like this thing, classical